Good
Good
afternoon.
afternoon.
Am I
Am I
audible?
audible?
Hello?
Hello.
Yes, yes, madam.
Okay.
Okay.
Audible.
So this is
So
week
this is
3
week three
problem solving
problem
session,
solving session,
Microelectronics device to
microelectronics device
circuit.
to circuit.
I'm Arpita
I'm
Biswas,
Arpita
a PhD
Biswas, a
scholar
PhD
in
scholar
electrical
in electrical
engineering
engineering
department from IIT
department from
Jodhpur.
IIT Jodhpur.
This is more details
This is
about
more
me
details
that
about
I
me
did my
that I
BTech
did my
from
BTech from
Maulana Abul Kalam
Maulana Abul Kalam
University of
University
Technology,
of Technology,
and I did my
and I
MTech
did my
from
MTech from
IIIT Jabalpur
IIT
in
Jabalpur
Micro
in
Nano
Micro Nano
Electronics, and
Electronics,
recently I am
and
pursuing
recently I am
PhD
pursuing
third year,
PhD third year,
and
and
in electrical
in electrical
engineering, and
engineering,
my
and
research
my
domain
research
is
domain is
chemiresistive
chemiresistive
biosensor
biosensor
fabrication.
fabrication.
So
So
this class
this
session is
class
every
session is
Tuesday
every
7 to
Tuesday
9 p.m.
7 to
So we are
9
going
p.m.
to
So we are
discuss
going
some
to discuss
questions,
some
and
questions.
if you are
And
if you are having
if you are
any
having any
doubts, so you
doubts,
can
so you can
ask me.
ask me.
So let's
So
start the
let's start the
session.
session.
So this is a
So this
question
is a
number
question
1.
number one.
In simple
In simple
BJT
BJT
inverter, in
inverter,
which
in
mode
which mode
voltage gain is
voltage gain
0?
is zero?
So please
So please
unmute yourself
unmute
and
yourself
try to give the
and try to
answer.
give the answer.
Saturation.
Sorry, I did
Sorry, I
not
did
get
not.
you.
Saturation.
In which
In
mode?
which mode?
Saturation mode.
Saturation mode
Saturation
and
mode.
Saturation mode.
okay.
Okay.
Anyone else?
Anyone else?
In which
In
mode
which mode
the
the
voltage gain
voltage
is
gain is
0?
zero?
Ma'am, common collector mode.
Actually, I'm talking
talking
about
about
active mode,
active mode,
saturation mode,
saturation
and
mode,
the
and the
cutoff
cutoff
mode.
mode.
Okay, ma'am.
So in which
In
mode
which
the
mode the
voltage gain
voltage
is
gain
0
is
when
zero when
in a simple
in a
BJT
simple BJT
inverter
inverter
structure?
structure?
Some would be
That is saturation mode.
okay.
Okay.
Anyone else?
Anyone else?
Pradeep P.
Pradeep P.
But it's the right
What is the
answer.
right answer?
Please unmute
Please
yourself.
unmute yourself.
At least try.
At least try.
Yes, madam. In BJT in saturation region, output voltage goes to VC is at almost 0. So whenever input more than cut-in voltage, output goes to 0. That's why gain is 0 in saturation mode.
Okay.
Okay.
Kavya.
Kavya.
Is it okay?
What is?
What is?
I'm going to
I'm
explain.
going to explain.
Just wait.
Just wait.
Kavya, what is the right
What is the
answer?
right answer?
In simple
In simple
BJT
BJT
inverter,
inverter,
in which
in
mode
which
voltage
mode
gain
voltage
is
gain
0?
is zero?
Kavya,
Kavya.
but is the right
What is the right
answer.
answer?
Please unmute
Please
yourself.
unmute yourself.
Okay,
Okay.
just a minute.
Just a minute.
Can you see the
Can you
slide
see
now?
the slide now?
Hello,
Hello.
am I audible?
Am I audible?
Yes, yes,
Okay.
audible.
So in
So
BJT,
in BJT.
okay.
Okay.
So in BJT
in
inverter,
BJT inverter.
Slide is not
Just-
seen.
just a minute.
That's fine.
I think all of you know about the
the
output input characteristics. It will take some time. This is the V output. Okay. And from this side, this is the V input. Okay. Then what happened? Have you seen this type of diagram? The input-output characteristics of BJT inverter?
Yes, ma'am. It is a VTC curve.
Yes. Just ignore my handwriting. And this thing is V output high and this thing is V output low and this is V input high and this is V input low. Sorry, V input low and this is V input high. So up to this, you all of you know, I think, the VTC curve, V input versus V output curve. So what happened in that region? Tell me what happened. Just a minute.
Ma'am, it is the cutoff mode of operation.
Okay, because here the the input voltage is very low. So when it is okay, and when it is less than 0.7, then in that case we can tell that it is in the BJT is in cutoff mode. And after that, okay, and after that, when the V input is greater than the VI high, in that case, in which mode? In that case, BJT in which mode?
Saturation mode.
It is in saturation mode.
And ma'am, this VOL is almost equivalent to VC sat.
Just a minute. Okay. This is cut off. Okay. So now tell me. And this is active. Okay. So what is the V output gain? AV equal to
V out by V.
V output by V input. So now tell me, in cutoff region, the AV is dependent on the V input or not?
V input
Up
is very low.
to, yes, V input is very low, and when V input is very low, just a minute, I'm drawing the circuit. This is the circuit. So here you can see that. I think there is some V input, or here the VCC, right? So now tell me, if the V input is very low, in that case, in cutoff region, any current will flowing from this RC.
No.
So in that case, what will be the output voltage?
It will be VCC.
VCC.
VCC will be the output voltage.
VCC. So up to that point, the VI high, the output is depends on the input or not. Whatever the input you are giving now, so output is dependent on this input voltage, or it is constant.
Constant, ma'am. It will be VCC only. It is
Only
not dependent on
VCC.
V
So
input.
it is not dependent on the V input. Okay. So in that case, the gain, as actually if the gain is del V output by del V in. So if the output voltage is changing with respect to change in the input voltage, in that case the AV. Okay. But if del V is just, if del V in here not changing now, it means if you are changing the input voltage, there is no change in the output voltage. So gain is simply 0 in that case also. You got my point?
Yes.
Samuel,
Yes, madam. Yes.
what is happening in the cutoff mode when you are changing the input? Here input is very low. So it is not affects on the output voltage, okay. But when it goes to the saturation mode, in that case also what happen, in saturation mode the V input, just a minute, to erase it. Now simply understand what happened in the saturation mode. When you are giving the input is very high, it means V input equal to VCC. What happened in that case? Tell me.
High current flows.
High current will flow. So what about the V output?
IC is equal to VCC by RC.
IC equal to VCC minus
VCC minus VCE
by RC. Okay.
minus.
But tell me, what about the V output here?
V out is VCE sat.
Yes. VCE sat. It means now the BJT is in saturation mode. Okay. It means and the value of the VCE sat, it almost 0.2. It is nearly 0.
0.3.
Yes, it is nearly, we can say that 0. Okay. So here also you can see that in that region, if you are giving the voltage greater than this VCC now, so there is not that much change in the V output. So in that region also the V output is not changing. So in saturation mode also the gain is what? In saturation mode
Gain is
0 na?
0.
Because gain is equal to del V output by del V in. So in cutoff mode and in saturation mode, when you are changing the input, we are not getting that much change in output. Okay, so it is almost constant. So in cutoff mode and in saturation mode, our gain is 0. Okay, so the right answer is cutoff mode and saturation mode. Okay.
Okay.
Just a minute. Now tell me what is the right answer. First tell me what is the noise margin. Do you have any idea about the noise margin?
Ma'am, noise margin is basically it is the means how much noise my device can withstand. That is basically by without changing my output. Means if I give my input as 1, it should be the output should not be reflected by the noise. So that much amount of noise that will not affect my output is called the noise margin.
Yes. So here noise margin is, the first option is the amount of noise the logic circuit can withstand. The second option is difference between the V output high and the V input high. And the third option is the difference between V input low and the V output low. And the fourth option is all of the mentioned. So what is the right answer?
B and C.
Madam, only option A is the answer for noise margin, madam. Difference between VOH and VIH is noise margin high. Difference between VIL and VOL is noise margin low. Noise margin is noise margin high minus noise margin low. For this question, the option is A, madam. Option is A, madam.
Actually,
B and C, madam.
Last option should be the right answer.
Okay. Can you explain?
Ma'am, because basically as sir has told, that is VOH minus VIH is the noise margin is high, and option C is for low noise margin, and the above is the definition, that is the noise the logic circuit can withstand. So
Yes.
all the three are coming as noise margin. So I think option B, last option will be the right one.
Okay. Samal, what is the right answer?
DC, madam, as per formulas.
Yes. Kavya, what is the right answer? Kavya, please unmute yourself.
Option A, ma'am.
Can you explain why not option B and option C? Actually, first option A is the definition of noise margin, but how you calculate the noise margin? There is any formula? So here the right option is option D, because the first one, here you can see this first one is the only the definition of the noise margin, and how you calculate the noise margin. If noise margin high, then tell me what is the value of noise margin high?
VOH minus VIH, madam.
Yes. V output high minus V input high. And noise margin low. Tell me.
VIL minus VOL.
V input low minus V output low. Okay. So this is the equation for how to solve this type of problem. It's the how to solve this, calculate the noise margin high and low. This is only the equation, so it is related to this noise margin. Okay, so the right option is option D.
Madam, but it is only independent, na? Difference between VOH and VIH, only noise margin high and noise margin low. But noise margin is noise margin high minus noise margin low, na madam?
No, when you are going to solve this type of equation or this type of problem, na, then you can see that noise margin high and noise margin low we have to calculate, and it is related to that noise margin, na. That's why
These are relevant options. That's why all the mentioned. That's what you want to say, madam?
Yes. All of them. Okay. So we are moving toward the question number 3. Please, all of you, at least try. Kavya and Samuel. Okay, question number 3. The VIL is found from the transfer function of inverted Y. So the first option is the point where the straight line at VOH end, the slope of the transition at a point at which the slope is equal to -1. The option C is the midpoint of the transition line. Option D is the all of the mentioned.
Ma'am, first option.
The point where straight line at VOH end. Anyone else?
Yes, ma'am.
So like previous question, I am thinking maybe option D, madam. Chances are there. Why? Because whenever VLL crosses, there if you calculate slope also will get -1, madam. Delta V out by delta V. My guess, madam. That's why I am saving option D, madam. I am saying that.
Option D.
Yes, madam. Maybe I
Okay.
may be wrong, but I got answers A and B relevant to that, but there is no specific answer for that. I am choosing D, madam.
Okay. Samuel, what is the right answer?
Just I am thinking, madam.
Okay, take your time. Kavya, what is the right answer? The VIL input low found from the transfer characteristic from the VTC graph of inverter of a BJT inverter, where you can find out the VIL value. The point where the straight line at VOH end, the slope of the transition at a point at which the slope is equal to -1. The option C is the midpoint of the transition line, and last option is the all of the mentioned. Those who are going for the first option, now tell me the point where the straight line at VOH end. It means
Yeah, answer, madam. Yeah, answer.
can you explain why A? Just let me draw. This is the just a minute. Just a minute. This is the V output input characteristic. Okay. This is the V input low. Okay. And this is V input high. V output low, and this is V output high. So now tell me VIN, this point. Okay, it's meant this point. Tell me this point. What information you are getting from this point? The point where the straight line at VOH end.
The input voltage, the low input voltage required to start conducting for the inverter is the VOH voltage.
Just tell me if VOH end, okay, just carefully listen. If the VOH end, okay, at that point, up to that point, it is in cutoff mode. It's mean slightly greater than this. It's mean that, okay. So it is entering into the active mode. Okay. If it is up to this or end of this VOH, so this is in cutoff mode. Okay. And if like it is not directly that, okay, it is slightly this. So if here it is ending and then small non-linear, then linearly it is going back. Now tell me, here it is ending. So V input low. V input low means slightly, if you are giving that much amount of voltage, so the BJT is on stage. So are you getting any clue that BJT is in on stage? If the voltage is very low, then first option, the point where the straight line at VOH end. VOH end means up to that point it is in cutoff mode. But slightly greater than this cutoff mode, it is entering, you are giving some input low voltage, so it is coming to the active mode. So in that point, what is the slope?
-1, madam.
-1.
If you calculate.
Yes. So slope is -1.
So option B will be the right answer.
Yes. So option B is the right answer. Now it is clear? Why option B? Why not option A?
Ma'am, can you repeat it, ma'am?
Can anyone explain what I have told?
Actually, you are saying that the point where the straight line VOH ends, before VOH ends, it should be in the cutoff region. But we are moving to the VIL. The circuit goes to the active region. That's why.
So we are giving small input voltage, so it is in active mode. Okay. Because before that it is in cutoff.
Yes, ma'am. Yes.
Now it is clear. And slope of this straight line is -1. That's why the right answer is option B. Because when VOH end, up to that point, it is in cutoff mode. And in cutoff mode, the input, the output is not depends on the input. So how much input you are giving, it is not affects on the output voltage. Okay. So when you are giving slightly the input voltage slightly greater than this cutoff voltage, then you are entering into the active region, and in that case the slope is -1, and this voltage is known as VIL. Otherwise, if it is the first option is, if it, the first option is the right answer, then VIL should be 0. I think VBE like 0.7 or something else. But here VIL, how we will solve a numericals, then it will be clear, more clear to you. Okay. So next we are moving towards the question number 4. The lower noise margin is given by, the first option is VOL minus VIL, the second option is VIL minus VOL, the third option is VIL minus VOL. Difference between the VIL and VOL depends on which one is greater, and the last option is all of them mentioned. So lower noise margin.
Direct question, madam. Option B from my side. VIL minus VOL.
Okay. Anyone else? What is the right answer?
Ma'am, option B.
Okay. Kavya?
Option C, ma'am.
Can you little bit explain why option C?
Ma'am, I think it cannot be negative. So,
Okay. Let's see.
the
Okay.
grade.
Okay. I'm explaining. Just a minute. Anyone else here?
Can I give explanation, madam?
Okay. You can.
Yeah, madam, actually, whenever amplifier, we are saying that the painful amplification, let us take a amplifier gain of 2, if input signal of peak to peak 4 volts, then output obviously 8 volts, madam, peak to peak. Then obviously average value will be 0. So option is lower than lower and higher than higher. VOH is higher than higher. VOL is lower than lower. So VIL minus VOL is the exact answer for lower noise margin.
Okay. From this graph now, can you tell me which one is the lower margin high and which one is the lower margin noise margin low? Just tell me. V output
So it's
high,
rightmost VIH, leftmost VIL, VOH, VOL. Okay.
V input low, V input high,
VOL.
V input high. Okay. V input and this side V output. Now tell me which portion is noise margin high and noise margin low. And we know that noise margin high is equal to V output high minus V input high, and noise margin low is V input low minus V output low. Now tell me which portion is noise margin high or noise margin low in this graph? Which region? It's when which area is defined noise margin high and noise margin low. Take your time, but at least try, then I will explain. If you are reducing the V up to VOH, V output high, then you are just reducing the value of V input high. Then what region you are getting?
Cutoff and active.
Okay, cutoff and
Active
active.
region part, madam. Active region part, I think. Correct, active region.
Cutoff and active is noise margin high.
Tell me, in this region.
This region is the low noise margin.
Okay. Now tell me what you will call this region, and what about this region? This
What
is
about VOH upper portion, madam?
this is
Not
1
1
and this is 2.
and this is
Wait,
2.
so 1 or 2?
So 1 or 2.
Noise margin high.
Margin high.
If you are calculating the
calculating
VOH,
the VOH,
V output high minus
output
V
high
input
minus
high,
V input
then you
high,
are getting which region? 1 or 2?
1 or 2?
2, madam.
V
Yes, ma'am.
output high,
Output high.
then V
Then
input
V
high.
input high.
Is 2, number 2 region.
Okay.
Okay.
And what about
And
the
what
number
about the
1
number
region?
1 region?
It is a low noise margin.
PIL
Yes.
minus VOL.
This is
This is
noise
VIL
margin
minus VOL.
low. This is noise margin
margin.
high. So if you are changing, I think the area will negative, but it is not possible. Na? That's why we are taking this V input low minus V output low. Now it is clear?
Now it is clear?
So this is the next question. Question number 5.
Question number 5.
Determine the noise margin of 5 volt
5
TTL
volt
inverter gate,
gate.
and these are the option. Noise margin high equal to 0.4 volt. Noise margin low is 0.4. Noise margin high is 2.4. Noise and so at first you have to calculate. So calculate this one, and then we are going to explain. Just calculate a noise margin high and noise margin low from this figure.
Option A, madam, 0.4 volts, 0.4 volts.
0.4, 0.4.
2.4 minus 2, 0.8 minus 0.6.
Yes, ma'am. Option A will be the right answer.
Option A is the
Okay. Kavya and Samuel, what is the right answer and how to calculate it?
so direct
Yes, ma'am.
substitution.
According to the
Formula.
according to the
Yes.
formula.
How you will calculate noise margin high?
high.
I have already
I have
shown.
already shown.
VOH minus VIH, ma'am.
Okay. And what is the value of
And what is
VOH
the value
here
of
mentioned?
VOH here
2.4.
mentioned? 2.4.
And VIH
And
is 2.
VIH is 2.
So noise margin high is equal to 0.4. And noise margin
And
low
noise
is
margin low is
also
also
VIL, which is 0.8, and VOL, which is 0.4. So the both value are 0.4. I have to write here, or I have to move next question.
Next question.
Okay.
Okay.
So this is the question number 6.
Number 6.
Define the mode of
Yes.
Yes, Samuel.
Previous one, which is answer? Previous one, which is answer? A.
Yes, the right answer
The
is
right
E.
answer is A.
Yes. How to calculate? Have you calculated this question? Or I have to write here? Samuel?
Not calculated. Formula is there, madam. I know. VOH minus VIH.
Yes, just see here. Just a minute. I'm showing.
Okay.
Like noise margin high equal to VOH minus V input high. So here you can see that the value mentioned. Just simply put the value 2.4 minus 2.
2.4 minus
2, so 0.4 volt. Okay. And the noise margin low is equal to what? VIL minus VOL. So it is the value VIL 0.8 minus 0.4 volt. Okay. So the value is 0.4 volt. Now it is clear?
Yes, madam. 0.4.
Okay. So this is the next question. Question number 6. Define the mode of operation when V input belongs greater than equal to VIL and less than equal to VIH. Now tell me what is the mode of operation? It is in saturation, active, or cutoff mode.
Madam, this is V1, middle, VIL.
VI means input voltage you are giving, which is greater than equal to VIL or less than equal to VIH.
Active region, ma'am. Active region.
What's in active region? Okay. Anyone else?
Cut-off region, madam. Cut-off region, madam. Cut-off.
Okay. Someone is telling cutoff. One of them is saturation. Kavya, what is the region here? Saturation, cutoff, or active?
Active, ma'am.
Okay. Anyone else?
Yes, madam. V input greater than VIL and less than VIH. Yeah. Yes, madam.
Ma'am, active region of operation, active.
Yes. Now see. Same graph. The VTC graph. Here we input low and we input high. So it is in that region. Okay? So in that region, if your V input belongs, then it is in active region. Okay? And if it is less than, see, equal to or less than, then it is also inactive, and it is equal to or equal to and less than of VIH, it is inactive, and also it is equal to or greater than the VIL, it is also inactive. So now we are getting that point, na? Up to VOH, we have solved the previous question. V output high. This is in cutoff, but when it is entering, it is equal to or gets slightly greater than the VIL. So then the slope is -1. So here the same. If it is less than this VIL, then which region? If VI is, then it is V input less than VIL, then which region?
Active region, ma'am.
Then it is in cutoff region.
Cutoff region, madam, less than.
Yes. And if it is, now tell me, VI equal to VIH, which region?
Active region, ma'am.
Yes, it is in active. Equal to or less than. See the symbol. And here equal to or greater than. Then both cases the BJT is in active. Okay. And if it is greater than VIH, in which region?
Active region.
The saturation.
That is greater than saturation.
V input is less than VI. Just a minute, sorry. It is in active region. Or if it is greater than. Okay. In that case, saturation. Because if it is less than, then it is in active mode. And if it is greater than, then it is in saturation. Up to this, do you have any doubt?
No, ma'am.
So this is the question number 7 in numericals. Find the static noise margin for a BJT inverter shown in the figure. So beta given, VVE is given, and VV when it is in saturation, its value also given, and VC is saturation voltage also given. So find out the noise margin here. Take your time, but at least try.
Noise margin low is VB is at minus VC is at 0.8 minus 0.1. So noise margin low is 0.7 volts, madam. Later one I am calculating noise margin high.
Or here 4 case will be there. So at first calculate. At first case you have to calculate the V output high, then V output low, then V input high, then you have to calculate the V input low. Then find out the noise margin high and then noise margin low. All the value are given here.
Ma'am, the V output high will be 5 volt. That is the VCC.
Okay. Then
and the V output low will be the VC set, that is 0.1 volt.
okay.
and then
And the VI L, that is the V input low, will be VBE, that is 0.7 volt.
No, VIL you have to calculate. I think VIL and VIH. Try. Then we will
VI
discuss.
is just calculated. It is coming as 1.4, that is IBRB plus VB. VIH is 1.4 volt. It is coming.
VIL. What is the value of VIL?
VIH is coming as 1.4 volt.
No.
VIL is 0.7.
VIL.
IL is 0.7. VBE act.
Try.
Ma'am, is VIL 0.7 and VIH is 0.8?
Kavya, your voice is not clear. Can you tell me again?
Ma'am, is VIL is 0.7 and VIH is 0.8?
no.
Here one point. Tell me, when V input low, you are calculating V input low. In that situation, how you are calculating? That's when which one is in saturation or something. Here you can see that the question also VC saturation voltage is given. VBE normal voltage when it is low na, then 0.7, and when VBE is in saturation. Just a minute.
Ma'am, your voice is not audible.
Just a minute. Now my voice is audible. Hello.
Yeah, fine, ma'am.
Here these two things we have to notice. VBE saturation and VBE normal voltage is given. So now tell me, when you are calculating the VIL, then in which voltage you are taking the VBE value? It is saturation or normal VBE value you are taking. When VBE will in saturation, when you are calculating VIL or VIH, only there is the.
In VIL, that is the low input, I think 0.7 would be considered.
No. At first tell me, when you are calculating the VIL, in that case, what is the value of VBE?
Yeah, transistor is moving from cutoff to active region. So that's why VIL is VBE active 0.7 volt.
0.7, yes, I also think so.
Yes, in that case, you are taking the 0.7 volt, okay? And when you are calculating the VIH, when you are calculating the VIH, you are giving the higher input voltage. In that case, what is the value of VBE?
0.8.
Yes, in that case, you have to take the VBE is equal to 0.8. Now calculate only same loop. This is the loop. Just a minute. You have to just take this loop. For both cases, when you are calculating. First case, when you are going to calculate the VIL, then just you have to take the VBE value 0.7, and when you are giving the V input high, in that case, VBE saturation. Okay, 0.8. Simply you have to do this. There is no hurry. You take your time and then calculate.
Ma'am, VIH answer is coming as 1.5 volt.
And what is the value of VIL?
VIL?
Kavya,
Pradeep,
Pradeep,
and
and Samuel.
Samuel.
VIL is 1.4 volt.
Yes,
Yes,
1.4 volt.
4 volt.
Pradeep, Kavya,
Kavya.
how to
Yeah,
calculate?
yeah, madam.
Calculate.
I have not calculated. Only I have checked the formula of VIL. That is VBX or like that, sir, based on the formula. That's why I have mentioned 0.7. VIH I have not calculated.
Okay, take your time.
Take your time.
Calculate.
Calculate.
Okay.
Okay.
Ma'am, the high noise margin, that is NMH high, is coming as 3.5 volt.
Yes.
Yes.
And
Noise
what
margin
about the
high.
noise
The
margin
margin
low?
low.
Yes, noise margin
Noise
high is
margin high is
3.5
3.5.
and noise margin
And
low
noise
is
margin low is
1.4 minus 0.1.
is
Is
1.3.
1.3 volts. Noise margin low.
Good. Yes.
Yes.
But others also try how to calculate. Take your
Take your time.
but at least try.
At least try.
Kavya,
Kavya,
Pradeep,
Samuel.
Not
Ma'am, actually this type of a question was given in our NPTEL assignment in week 3, but there only the VB's value was given. So that's why in that case the VIL was directly coming as 0.7. But as VB and VB said both the values are given, so that's why separate calculations are required in this one.
Yes. Yes, Kavya.
Yes, Kavya. Ramakant.
What is the right answer? Please unmute yourself. At least try. I'm not expecting that all of you are going to give the right answer. But at least try, then I will explain. Ramakant, Kavya, Samuel, and Pradeep. Pradeep is trying. Samuel, and Kavya. I think up to this you have. So, at first, case 1. Here we know the transfer characteristics. The input. Input low, then we input high. And this is V output low, and this is V output high. So first case you have to take when we input is very low. All of you have calculated the first value. Am I audible?
We were in a confusing position how to take.
Just first, this is inverter. So first take V input 0. Then tell me what is the value of V output. Kavya,
Samuel. VCC.
In
5
that
volts.
question, yes.
5 volts, ma'am.
Okay.
Okay.
So in that case,
In that case,
BJT
BJT
on.
Cut off region.
Sorry, off.
off.
It is in
It is in
cutoff
cutoff
region.
region.
Okay.
Okay.
So in cutoff region,
Cutoff
here you
region,
can see
here you
that
can see
if
that
V input
if
is
V
low,
input is low,
V input is 0 means V input is
V
low.
input is low.
In that
In
case, the
that
V
case, the
output
V
is
output
VCC.
is VCC.
Okay.
Okay.
Because
Because
no current is
no current
passing.
is passing.
Here no current
Here
is
no
passing.
current
So
is passing.
directly
So directly
VCC equal to the
VCC
V
equal to the
output.
V output.
V output
V output
equal to
equal to
VCC,
VCC,
which is 5 volt.
5 volt.
Okay.
Okay.
Then this is the
Then this is
V
the
output
V output
high.
high.
5 volt.
5 volt.
The first
The first.
equation. And now take
And now take
the second
the
case.
second case.
Case 2. What is the case
What
2?
is the case 2?
First case is
First
V
case
input
is
equal to
input
0.
equal to 0.
No, the second we are
Second,
at
we
first
are
we are going to calculate the output voltage. V output low we are going to calculate. So in that case also V input is 5 volt.
5 volt.
Now tell me what
Now
is the
tell me
value
what is the
of
value of
V output?
V output.
If V input
Zero,
it means no, it's
No,
near
it's
about
nearly
zero, but it is not proper zero. Okay.
zero. Okay.
In that
In that
condition, the BJT is in the saturation mode. Okay.
Okay.
So yes,
Yes.
V CE sat.
Sat.
CE saturation.
0.1 volt. 0.1 volt.
No, it is yes, you can take point.
Point.
Okay.
Okay.
Point on.
Point on.
Given.
It is
Yes,
mentioned
it
in
is
the
mentioned.
question.
Okay, okay, it is
Okay.
mentioned.
Mentioned.
Okay.
Okay.
0.1 volt.
Volt.
Okay.
Okay.
Ma'am, if
So-
they are not mentioned,
Then you can take
You can
0.2.
take
If it is not mentioned, then
If it is
0.2 you can directly.
0.3 for silicon and 0.1 for germanium. We see is at standard values.
Okay.
Okay.
Then this is the
Then this is the
V
V
output low.
output low.
This is the 0.1 voltage.
voltage.
So up to this,
So up to this,
you have any
do you have
doubt?
any doubt?
This is the question 2.
2.
So what we are
What
getting,
we
we
are
are
getting,
mentioning.
we are mentioning.
Just a minute. First we have
First we
got V output high equal to 5 volt
5 volt
and
and
V output low is equal to 0.1 volt. These two things.
These two things.
I'm going to
I'm
erase
going
it.
to
So
erase it.
do you have
So,
any
do you have any
issue?
issue?
1 minute, madam. 1 minute. Just 1 second.
Okay.
Okay.
I will take just photo. Okay, madam.
Okay.
Okay.
So next we are going to calculate the V input low and then V input high. So now just a minute. Now
Now
tell me, when the V input is low, how to calculate the V input now?
input now?
Just we have to
Just we
take
have
this
to
loop.
take this loop.
If V input is low,
If V
then
input is
very
low,
small
then
amount
very
of
small
current,
amount of current,
IB,
IB,
very small.
very
We can,
small. You can
tell that it is
tell that
V
it is
minimum.
V
Okay.
minimum.
So
Okay.
if V
So if
input
V
is
input is
very low,
very low,
so IB
so
minimum
IB
is passing
minimum
through
is
this
passing through
RB.
this RB.
Okay. And in that
And
case,
in that
VBE
case,
equal to
VBE equal to
0.7.
0.7.
So just take the
So
loop.
just take
Now
the
tell me
loop.
the
Now tell me
equation.
the equation.
What is the equation
What
in
is the
that case?
equation in that case?
IB RB plus VBE.
Here V
Here
input you are getting,
input you are
giving na.
giving
So
na.
V
So
input
Minus V in VIL minus IBRB plus VBE. minus IBRB.
Here minus is there, na?
there, na?
Like here
Like
it is
yes.
positive and this is negative. So here positive and negative. You are taking this loop. It means negative to positive we are going. Then we are taking it positive. Now tell me the loop.
Minus IRB, VIL minus
Minus
IBRB.
IB, which is very small amount, so we can tell that will be in minimum, and then RB, then minus
Plus VB. Minus VB.
minus VBE equal to 0. VBE here 0.7 plus IB minimum RD. Now tell me how you will calculate the IB value. What is the value of IB? Tell me.
IC by beta. IC by beta. IC we have to calculate, madam.
Yes, we have to calculate the IC. Now tell me how you
I is
will.
equal to beta.
Yes. Here we have to find out the value of IB. So that's why we have to calculate the value of IC, because IB minimum equal to IC
by beta.
which is saturation mode by beta. Okay. So what is the value of IC saturation? So what is the value of IC saturation?
5 volts minus 0.1 by 70, madam.
So IC value is VCC minus
VC sat by
VCE sat by
RC.
but RC. Now what is the value of IC? Calculate it.
4.9 milliampere.
4.9 milliampere. All of you calculate and tell the answer is matching or not.
Correct, match.
Okay. Just put the value 4.9 milliamps by beta value 70. Then what is the value of IB?
0.07 milliamp.
0.07 milliamps.
Yes, ma'am.
Okay.
Yes, ma'am. 0.07 milliampere.
Now just put the value here. 0.07 milliamps
10 power minus 3
and RB value
into 10 into 10 kilo
3.
cube. 1.4.
Kavya, up to this, do you have any issue or any problem?
No, ma'am.
Have you calculated or have you written it how to calculate the VIL?
Yes, ma'am.
Okay, so write down this. Then we will calculate the next one. So here we got VIL is 1.4 volt. I'm going to erase it, so write down there. Then Pradeep, do you have any doubt?
Yeah,
or
madam,
is
okay, fine.
clear? Oh,
No, clear, ma'am. Clear. Pending calculation is VIH.
Yes. So can I erase it?
Yeah, fine, ma'am. Fine, erase.
Yes, madam.
Ma'am.
Very noise is coming actually.
I
I
think
think
Samuel,
you
you
have
have
to
to
mute
mute when you are
when you are
not
not
talking.
talking.
Na?
Na?
I think now it is clear. Yes, yes, yes. Now tell me how we are going to calculate the VIH, V input high. We are taking the same loop. Okay. We are taking the same loop, and now tell me what is the equation when we are giving the input high. What happened in that case? Yes. VIH minus IB. Um, my slide is visible or not? Just a minute. What happened? Just a minute. I lost my connection. Just a minute. Actually, I lost my connection. Just wait for 2 minutes. I have connected it from laptop now, and it is from phone, so it will take some time. Just a minute. Connection is interrupted. Now can you see my
Now can you
slide?
see my slide?
Yes, ma'am, yes.
So
So
we're discussing
we're
about the
discussing about the
VIH.
VIH.
So
So
again,
again,
take this
take
loop.
this loop.
Madam, you can write down directly VIH equation, madam. No problem.
No issue.
No issue.
Okay.
No issue, madam. No issue.
VIH equal to,
VIH minus IBRB
just a minute.
Just a minute.
VIH equal
VIH
to
equal to
RB
IBRB plus VB.
IBRB plus VB
minimum
SAT, I think so.
plus
plus
PVE
PVE
saturation.
saturation.
SAT.
Okay.
Okay.
Then what is the value of
What is the value of RB? 10,
10 kilo ohm.
3.
RB is
RB is
0.07
07
0.07
and 10 to the power
and 10 to the
3
power 3 minus 3.
then VB
plus 0.8.
0.8.
0.8.
So
It will come as 1.5 volt.
1.5.
so
So
noise
noise
margin
margin
high equal to,
what is the equation?
VOH minus VIH.
and what is the
That is
value of
What is the value of
VOH?
VOH?
3.5
5 volts minus 1.5.
5
5
minus
minus
1.5.
1.5, 3.5.
3.5 is the answer.
Yes.
Yes.
And noise
Noise margin low equal to
V input
V input
high.
high.
Sorry, V input
Sorry,
low.
V input low.
V input low
V input
minus
low minus
VYL.
V output.
1.4 minus 0.1, 1.3 volts.
So it is
1.3 volt.
So please write
So
down
please
this.
write down
Then
this. Then we are going to move towards the next question.
Madam, if you see the pictorial representation, only 0.1 volts is the region with for active region based on the calculations.
So you're telling
So
about
you're telling
one,
about
yes,
one, yes,
V input high
V
and V
input high
input low.
and V
Yes.
input low. Yes.
If you draw
If
this,
we draw this,
yes.
yes.
Let's draw this.
Let's draw this.
So here, what is the
Here,
value of
what is the value of V input high?
1
Sorry, V input low is
1.4,
1.4, I think.
And
Oh, yes,
V
1.5 is the
1.5.
1.5.
So only
So only 0.1.
This voltage is
This voltage
0.4.
is 0.4.
One is the active
One is the
region.
active region.
This is cut
This
off.
is cut off.
And this is
This is
saturation.
saturation.
Kavya,
Kavya,
is it clear?
is it clear?
Kavya?
Yes, ma'am.
Yes, ma'am.
Okay.
VH and VOH values.
But someone?
But someone?
VH and VOH values.
VOH 5 volts and VOL 5.1 volts.
Yes,
Yes.
this is a
This is a
VOH now. So
VOH
VOH
now. So
equal to
VOH equal to
VCC.
VCC.
So what is the value
So what is the value of VCC?
5.
5.
And here we have calculated the value of
the value of VOL.
So what is the value
So what is the value of VOL?
0.1.
This is at 0.1 volts.
We see
We
saturation.
see saturation.
So 0.1
So
volt.
0.1 volt.
So please write down.
Please write down.
Then we are going to move towards
the next question.
There are some
easy question next.
I think in the previous day
also we have calculated
this type of
this
question.
type of question.
So write down.
Write down.
Okay, madam.
Kavya,
Kavya,
have you written?
have you written?
Or I have
Or I have to wait?
Pradeep?
Ready?
No, ma'am.
Yeah, mine completed, madam. You can proceed for further question.
Okay.
Okay.
Kavya?
Kavya,
Wrote it down, ma'am.
Okay.
okay.
Samuel,
Samuel,
Kavya.
Kavya,
Ravikant?
Ravikant,
Ramakant.
Ramakant, sorry.
Ramakant?
Ramakant,
Okay, madam.
Okay.
okay.
So this
So
is
this is the next question.
This type of
This type of question in previous class we have solved.
So
I think all of you can give the answer we have done in the previous class.
So
So for a transistor beta is given and voltage drop across 1 kilo ohm is given. I just only change the value.
So I
So I
think
think
what we can give
you can give the answer. So tell me what is the
Ma'am,
Find
answer
out the
will be
base
answer base current?
16.66 microampere.
question number 8.
Question number 8.
16 point.
16 point.
666 microampere or 0.016 milliampere.
Yes.
Yes. 0.016
Others?
Milliampere.
What is the
What is the
how to calculate
how
at
to
first? Tell
calculate
me.
at first? Tell me.
Find the base
Find the
current
base
for the
current
common
for the
emitter
common
connection.
emitter connection.
Ma'am, can I say?
Yes.
Yes.
Ma'am, we can easily find the value of the IC collector current as RC is given and the voltage drop across RC is given. So that is 1 volt by 1 kilo ohm will be the value of IC, which is 1 milliampere. So if I get the value of 1 milliampere IC, the beta value is given as 60. So IB is equivalent to IC by beta. So 1 by 60, which will come as 0.016 milliampere base current.
Kavya,
Kavya,
now we can calculate.
now we can calculate.
Here the
Here the voltage drop is given and the resistance value is
So
given.
now tell me,
So now tell me what will be the current
flowing through this
flowing through this
resistance.
resistance.
So
So
It's a simple calculation, madam. Voltage by
Yes.
current will
Yes.
give IC. IC
So
by
IC
beta will
equal
give
IC
IB,
equal
madam.
to
1 by
1 by
1 kilo.
1 kilo ohm.
So this value is
This
1
value is
milliampere.
1 milliamp.
and then
And IB is 1 milliampere by 60.
beta equal
Beta is given.
IC by
IC by
IB.
So what is the
So what is
value
the
of
value of
IC?
IC?
IC is
IC
1
is
1
milliamp
milliampere by
60.
60.
So what is
So
the
what is
value
the value of
of
1 by
60?
60?
0.9.
0.0166 milliamps. I think this is the value of IB.
So please note
Please note down. Then we'll move toward the next question.
Next 2-3
Next 2-3 question is same as the previous class.
The numericals
The numericals we have solved.
Then some
Then some theoretical question we will be going to discuss.
Please write down.
Please write down. Then we'll move towards the next question.
Write down.
Write down and comment that.
Madam, there is one 8th question, madam, in the assignment. Such type question can you?
I think yes.
I
Last
think
time
yes, last time we have done this
question.
type of question.
So who have
Eighth
carefully
question.
listened this question, I think this type of problem easily can solve.
Excuse me, madam. In our today's in assignment 3, question is on NMOSFET, madam.
Sorry, Samuel,
Samuel, your voice is not clear to me.
Assignment
In a week
Assignment three.
assignment, there is a 8th question, madam, based on NMOSFET. Such type of problem can you solve, madam?
MOSFET related.
MOSFET related.
MOSFET related one question is there given in the.
There is some next we are going
Next we are going to discuss some MOSFET related question.
Okay.
Okay.
So
Okay.
next
There are I think 4-5 question of MOSFET related.
but
Some of them are relatable to the theoretical and some of the numerical.
And also if you
have any other doubt, then in the next class we can put some of the question from the MOSFET. Okay.
Shall I read that question, madam? 8th question type?
Sorry. What?
In question 8, NMOSFET based ID, VD and VTH, UN, COH, W by L, based on that one problem is there. In MOSFET.
Here only we
Here
are
only we are
doing
doing the
assignment
BJT.
question, sir. We are not supposed to discuss before
Yes,
this,
yes,
sir.
yes.
Yes, yes,
Only we
yes.
should apply,
Before
sir. We should
assignment
apply.
submission,
we
na,
can't
we
discuss
can't
about
discuss
this
about
question.
this question.
Then I can
Then
directly
I
put
can
this
directly
question
put
I
this
can
question I
discuss
can
there, na?
discuss there. Na?
I can discuss the
I can
relatable
discuss the
question, but
relatable
directly
question,
from
but
the
directly from the
assignment,
assignment,
I can't do that.
I can't
We
do that.
cannot discuss, and only we can apply whatever we have learned, sir. That's all, sir.
Yes.
Yes.
Okay, related. Related.
So I think this
So I
question
think this
also,
question
this type
also,
of question
this
we
type
have
of
solved in
question
the
we have
previous
solved in the
session.
previous
So
session. So
calculate
calculate
the base current
the
and
base
the
current and the
collector emitter
collector
voltage.
emitter voltage.
And we have
And
discussed
we
how
have
to
discussed how
calculate
to
the
calculate the V E
VCE
VCE
and the
and the
base
base
current.
current.
Just calculate
Just
it.
calculate it.
Here
Here I have just changed the alpha value
and the
and the
VCC
VCC
value,
value,
and all
and
the
all the
things are
things are
same
same
as the
as the
previous
previous
class.
class.
So it
So
will
it will
also
also
check
check
how
how
carefully
carefully
you have
you have
listened in
listened
this
in this
class.
class.
Who have
Who have
listened
listened
carefully, I
carefully, I
think
think
those
those
who
who
can
can
give
give
easily the
easily the
answer.
answer.
The
The
transistor is connected in a common emitter configuration in which
Collector
collector
supply
supply
is
is
10
10
volt
volt
and
and
the
the voltage
voltage
drop
drop
across
across
the
the
resistance
resistance
RC
RC
connected in the
collector
collector
circuit
circuit
is
is 0.5
0.5
volt.
volt.
Okay,
Okay,
so the
so the
value of
value of
RC is
RC
given,
is
which is
given, which is
800,
800,
and the alpha
and
value
the
is
alpha
given.
value is
So
given.
calculate the
So
collector
calculate the
emitter
collector
voltage and the
emitter
base
voltage
current.
and the base current.
Same way
The
you
same way
have to
you
do.
have to do.
At first
At
calculate
first
the IC
calculate the
value
IC value
and then calculate
and
the
then
VC
calculate the
value.
VC value.
And if you
Ma'am, the
And if
VC value is
yes,
yes,
what is the
the
value of
what is the
VC
VC?
value
value
of
is
VC?
coming as 9.5 volts.
Yes.
Yes.
And what is the value
And
of
what is the value
And
IC?
of
the
IC?
IC value is 0.625 milliampere.
Okay. And what
Okay.
is the
And
base
what is the
current?
base current?
Base current is coming as 0.032 milliampere.
Yes.
Yes.
Yeah, I
And
see by
others?
beta,
Others?
madam. Beta is equal to alpha by 1 minus alpha. If I am placing, I am getting the beta value. So I see by beta getting base current. Whatever
Beta
sir
is
said, that's
19.
correct. Yeah, whatever sir said, that's correct, madam.
Thank you, sir.
Okay.
Okay.
Others? Please
Others?
calculate it.
Please
I'm coming
calculate
back
it.
in
I'm
1
coming
minute.
back in
Just a
1
minute.
minute. Just a minute.
So all of you have
So all of you have
calculated this
calculated this
question?
question?
Yes,
Kavya?
ma'am.
Kavya?
VC, ma'am, VC is 9.5 volts.
Yes.
Yes.
See,
See,
here
here
VCC is given.
VCC is given.
This 10 volt.
This 10
And
volt
this
and
voltage
this
drop is
voltage
also
drop is
given.
also given.
So
So
what is the value of
what is the
IC?
value of IC?
because resistance
Because
value is
resistance
given
value is given
and also the
and
voltage
also the
across this
voltage
resistance
across
is
this
given. What
resistance
is the
is
value
given.
of
What is the value of
IC?
IC?
6.25 6.25 into 10 power minus 4 volts, ma'am. I mean, amperes, ma'am.
What is the
What
value
is
of
the value of
0 0.625
0.625
milliamps, right?
milliamps? Right?
Just you have to take
Just you
this
have to
loop.
take this loop.
Right, madam.
Okay.
Okay.
So 10
So 10
VCC
BCC minus
0.5
0.5
minus
minus
VCE.
VCE.
What is the value of
What is the
VCE?
value of
Yes,
VCE?
it is
It is 9.5
volt.
volt.
Okay.
Okay.
Then you have to.
Then you have to.
This is the first
This is the
question.
first question.
Yes, the VCE
The
value.
VCE value. Oh,
9.5.
9.5. Then you have to calculate this
IV.
IV.
That first
That
calculate
first
the
calculate the beta value,
which is
which is alpha
alpha
y 1 minus alpha
0.95
0.95 by 1 minus 0.95.
and this is value
And
is
this is value
19.
is 19.
Okay.
Okay.
So
Okay,
what is
madam.
the
Value of
beta
beta
ICY
ICY
IV?
IV.
Now tell me the value
Tell
of
me the
IV.
value of IV.
ICY
ICY beta.
So IC is
IC is
0.625
0.625
milliamps.
milliamps.
By beta value
By
is
beta value is
19.
19.
So the
The
value
value
is
is
0.0328
0.0328
milliamps.
milliamps.
So write down.
So write
Then
down.
we will move
Then
towards
we
the
will
next
move
question.
towards the next question.
Completed, ma'am.
So now
So
calculate
now
this.
calculate this.
Determine the
Determine the VCV value.
So you have to
So you have to
find out this
find
value.
out this value.
And this type
And
of
this type of question already we have solved. I just changed the value.
And beta is
And beta
given.
is given.
Silicon
Silicon transistor.
So you have to find
You
out
have
the
to find out the VCV.
Ma'am, the VCE value is means the collector to emitter voltage value is coming as 5.7 volts.
Okay.
Okay.
And the VB value is VB is, ma'am, I have to consider 0.7 volt base to emitter voltage. Okay. Then, ma'am, the answer that is the VCB is coming as 5 volts.
Yes.
Yes.
Now tell me how
Tell me how you have calculated Samuel.
How to calculate
How to
this?
calculate this?
What, madam? Once again.
How to
How to calculate
the VCB
the
value?
VCV value?
VCE minus VBE.
Okay.
Okay.
So
So
first beta is
beta
given.
is given.
Have to find VBE first.
And take
And
this.
take this loop.
Now tell
Now
me
tell
what
me
is
what
the
is the value of IC
and how to calculate
and how
it.
to calculate it.
Ma'am, first we have to find the value of IB, that is the base current. The base current, if we take the input loop, it will be VBB minus VBE by RB. So VBB is given as 5 volt, 5 minus VB, that is 0.7. So 5 minus 0.7 by 10 kilo ohm. The IB value is 0.43 milliampere is coming.
Yes.
So as we
From
give
the
the value,
first,
This is the first
this is the
loop.
first
So
loop.
if you are
So
taking
if you are taking from this side 5 minus
IB
zero point
IB
0.7.
RB
RB
minus
minus
VBE
VBE
0.7
0.7
equal to 0, right?
0, right?
So IB
So
equal to
IB equal to
4.3 by
4.3 by
10 kilo ohm.
10 kilo ohm. What is the value of? I think 0.43 milliamps.
Milliamps, yes.
Okay. So now calculate the value of IC.
IC, ma'am, it will be beta times IB. So beta is given as 100. So 100 into 0.43 milliamps, that is 43 milliamps. So ma'am, if I get the value of IC, then we can use the output loop that you have given in the output side. So we will be getting the value of VC equivalent to VCC minus ICRC.
VCC minus
ICRC will be value of
ICRC
yes.
minus
Ma'am, 100 into IC.
Yes, sorry.
yes, sorry. IC. This is IC. Yes,
This is 0.
this is 0.
And then
here
VC
we
value
here we
will
have-
come
But
as 5.7.
This is 0. Then we know that VCE equal to VCB plus PBE.
Then what is the value
And what is the value of VCB? 5.7 minus 0.7. The value is
5 volts.
5 volt.
Up to this, it
Up
is
to
clear?
this, it is clear?
Kavya?
Kavya?
Clear, madam.
Kavya?
Yes, ma'am.
Clear, madam. Clear, madam.
Okay.
Okay.
So now,
So now tell me
the state
of second order effect in bipolar transistor. Do you have any idea about the bipolar second order effect?
Yes, ma'am, can I try?
Yes.
Yes.
The bipolar effect, first of all, we can use about the base peak modulation effect that happens when we are increasing the reverse bias in the collector to base junction. That is, the VCB is taken as reverse bias during the active mode of operation, and the emitter to base is forward bias. So if we keep on increasing the reverse bias effect of the base to collector, then the due to reverse bias increase, the depletion layer of the base to collector region will also increase. As in reverse bias, the depletion width will increases, as we know. So if we keep on increasing the value of the reverse bias, the depletion layer width increases. As a result, the effective base width will decrease. So if the effective base width decreases, then at a time will happen that all the carriers from the emitter side will directly pass to the collector side, and the base carrier recombination will reduce, and all the carrier will go to the collector side. So that is basically the base width modulation. So we will be getting the early effect, early voltage will come, and as a result we will see that with increase of the VCB, my current will also increase. So we will be getting a slow increasing slope of the IC by increasing the VCB. Sorry.
Okay.
Anyone else?
Do you have any idea about the second order effect in bipolar transistor?
And then another thing I want to mention along with this, that is, if we are increasing the reverse bias, so as my beta is increasing because all the carriers are going to the collector. So due to this, the beta is increasing, the current gain is increasing, and due to this, as huge amount of current is going to the collector, so power dissipation is becoming more in the collector end. So as a result, a thermal runaway effect will arise. Thermal runaway means due to the self-heating will take place. So the collector side will be getting self-heated, and my device might get destroyed due to the self-heating of thermal runaway.
Also, have you
Heard about the
the avalanche breakdown?
Yes, ma'am. Avalanche
Yes.
breakdown Sarah has
Yes.
taught us.
Yes.
Yes.
Uh,
Okay.
Where the minority carriers will collide with each other, and it will break the covalent bonds, and multiplication of carriers will take place because of the reverse bias. Majority carriers cannot move through the depletion region, but the minority carrier from the base and collector will be attracted in the opposite sides. Means minority, if we are talking about the NPN transistor, so the N-type collector will be having minority as holes, and the P-type base will be having minority as electrons. So due to the increase of this reverse bias, the holes will come towards the base side, and the electrons from base will go to the collector side. So it will basically collide with the covalent bonds of the crystal lattice, and as a result, it will break the covalent bonds, and free carriers will be generated. So one carrier will break one covalent, carrier will be generated, then it will break another So multiplication of the carrier generation will take place.
And
And when we are increasing the reverse bias voltage, suddenly the current will increase. Okay.
Yes, ma'am.
So
Current will increase.
this is called the avalanche breakdown.
Yes, ma'am. Average breakdown of the device.
Good.
So
So
anyone
have
have
any
any
issue or
do you want to
understand anything else? Because
sure
Saurabh
give
gave the answer
correctly.
correctly.
Kavya,
Kavya,
Pradeep,
Pradeep,
Yes, madam. I understand one is thermal runaway, another one is early effect, and third one is avalanche breakdown. Madam.
yes.
yes.
Sarojini,
Sarojini,
have you understand?
have you understand?
Or we can
Or we can go for the next question.
We can go for the next question.
So this is also
So
a
this is
basic
also a
question.
basic
So
question.
please solve
So
this.
please solve
For a
this.
single
For a
state
single
transistor
state transistor amplifier, the collector load is given.
RC is 2
RC is 2
kilo
kilo
ohm
ohm and the input resistance
input resistance
RI
RI
is
is also
also
1
1
kilo
kilo
ohm.
ohm.
So if the current gain is
70, then calculate the voltage gain
amplifier.
of the amplifier.
I think this
I think
this type of question also we have solved in the previous
class.
Please solve.
Please solve. What is the value of voltage gain?
See,
See,
here the
here the beta
given.
is given.
Current gain is
Current gain is given.
RI
RI is given.
1 kilo
1 kilo ohm.
RC is
RC is given. 2 kilo ohm.
Then
What is the value of
VP?
VP?
VB will be considered
minus
as 0.7.
You can directly calculate here, no? The AV equal to beta into output voltage by input voltage. Add input. So what is the value of beta? 70 is 2 by 1 kilo ohm minus 40.
Have you understand?
Have you understand?
Someone?
Someone?
Madam, here it is not given. C amplifier is not given, no, madam. Like beta is for C amplifier. You can take.
So can we move
to the next question?
Yes, ma'am. Yes.
Yes, madam.
So this is the question
This is the question number 13 for an NPN transistor.
Yes, Shoro.
Yes, Shoro.
Ma'am, the answer will be C. 49 milliampere.
Okay.
Okay.
Anyone else?
Anyone else? What is the right answer?
Can you explain?
How you calculated?
Yes, ma'am, I can explain. Actually, ma'am, we have to consider the IC current first. IC current will be the formula of IS, that is a reverse saturation current, into epsilon of VB by VT. So VB value is 0.7, and the thermal voltage value from the KT by Q formula, we know that at room temperature the value is 26 millivolt or 0.026 volts, something like that. So if we put the value of IS as 10 to the power minus 13, it is given in the question, into epsilon to the power 0.7 by 0.026, then we will be getting the value as 0.4, almost 49 milliampere. and as the collector and base is shorted together, so the collector current will be almost equal to the base emitter current.
Base current. Yes.
Base and collector are shorted, so the I is almost equivalent to IC, so that's why the answer will be 49 milliampere.
So you have to just direct calculate the I equal to I saturation into E to the power PVE fine into PT.
Eta will be 1 in this case, minus 1.
Yes. Into the minus 13. Deliver dB is 0.7 by 1 into 26 millivolt. Okay, let's convert it 26 millivolt and then 1. So you will get almost nearly equal to 49 milliamps. The right answer is option C. Do you have any doubt? Samuel and Pradeep? Or we can move towards the next question.
No, ma'am. No, ma'am. Understand.
Okay. So, what is the next? The next question is in the figure. All transistors are identical and have a high value of beta. The voltage VDC is equal to. What is the right option?
Ma'am, 5 volts.
Okay. Tell me how you have calculated.
1 minute, ma'am. Actually, here as the beta is large, so we are considering the IC is equivalent to IB. So in that case, if the value VDC is basically my output voltage, so it will be equivalent to the VCC minus of collector current into resistance. So that is 10 volt is supply. 10 volt is the supply voltage, and we can 10 volt is supply voltage. Current will be 5 into the resistance is 1 kilo ohm. So 10 minus 5 into 1 kilo ohm. So we will be getting 5 volt as the VDC value.
Someone have you understand what he said?
Yes, madam. For telescopic connections, only we are getting first case output is total resistance, total output.
Okay. So from this 1 kilo ohm resistance, 5 milliamps current is flowing. So what happened in that case? I VDC equal to just simply 10 minus the resistance value 1 kilo ohm and into 5 milliamps. Okay. And VDC equal to 5 volt. This is the right answer. So can you move to the next question?
Yes, ma'am.
So now tell me what is the right answer of this 4 biasing circuit shown in the figure for BJT. Indicate which one can have the maximum bias stability.
Ma'am, option A will be the right answer because option A is symbolizing the voltage divided bias or the self bias. So we note that in the voltage divided bias, we are having the stability as 1. So which is the most stable design.
Samuel, what is the right answer?
Just thinking, madam. Yes.
Okay, take your time.
Option A, madam, is the correct answer.
Why?
Yeah, it is a common emitter, self-bias, madam. Out of biases, all biases, common emitter, self-bias will give more stability, madam.
Yes. So the right option is option A. So to transform the following layout, Samuel, you can mute yourself when you are going to give the answer. In that time, you can unmute. To transform the following layout of structure into a circuit symbol. So which one is the right answer? Pradeep?
Madam, I am just checking the structure, madam. I am just checking the structure, madam.
At first see the base is connected with the P plus
Madam, option B is the answer, madam. Option B is the correct answer.
Can you little bit explain why option B is
Yes,
the
madam.
correct
Yes,
answer?
madam. I am checking for emitter at which point and collector at which point and base at which point. After that, between there is a junction between the base and collector region. What is the junction? I am checking. So far, with respect to that, I am telling option B, madam.
Yes, the right option is option B. Here you can at first check B is P plus, okay, and emitter is N plus, and collector is also N plus plus. So only these two figure. This connection is happening. The emitter is N plus plus. This means here the direction. Okay. So and then see the
diode connection where it is connected to N plus. I am checking. I checked. That's why I am saying.
Okay. So the right option is option B. So next question, number 17. Consider the following statement for a metal oxide semiconductor filled transistor. The statement P is as channel length reduces, of state current increases. Statement Q as channel length reduces, output resistance increases. The statement R is as channel length reduces, threshold voltage remain constant. Or statement S is as channel length reduces, on current increases. So which of the above statements are incorrect? So which is the wrong information?
P and R.
Can you little bit explain?
Actually, RD is equal to 1 by lambda D, madam. Output resistance is equal to 1 by lambda ID. Lambda is channel length. So option statement Q is correct, madam. Wherever Q is there,
if the channel length reduces, output resistance will increase.
Yeah, that's fine, madam. Q correct. Statement Q correct. You are asking for incorrect, na, madam?
Yes,
Q is
I'm
not
asking for
correct.
incorrect.
Q is incorrect.
Can you explain little bit?
Ma'am, basically, if the channel length is reducing, that is, it happens when it is in saturation mode of operation. So during the saturation mode, my current will increase. So the output resistance, I think it reduces.
Yes, the output resistance will reduces.
So it is not
another one?
correct. And another one,
Yes.
that is the threshold voltage will not be threshold. Actually, when we are reducing the channel length, that is during the saturation mode. So the threshold voltage will not be constant. I think it reduces threshold voltage. Means with more less threshold voltage, that
Less
operation
threshold voltage is required
less
to operate this. Yes. So option C is the right option. Okay.
Correct, madam. Q and R, channel length and threshold voltage and output resistance relation. Correct.
Yes. Okay. So next question is the figure shows the band diagram of a MOS structure, and the surface region of this MOS is in inversion, accumulation, depletion, or flood band.
Ma'am, it is in accumulation.
Pradeep?
Yeah, I'm not getting, madam. I'm checking how the energy level is moving. I'm checking.
Yes.
Flat band and inversion is not possible. Oh, I think it is depletion mode, because flat band, the bands are not flat, so flat band condition is not possible.
Not possible.
Inversion will take place when the band bends downwards, then the inversion will take place. So here the upward bending of bands is there.
Here you can see that. Just a minute. Here is the QB, and here it is the band it is bending this side, and also here. See carefully.
Okay, ma'am, it is an inversion because the 5B and 5B, the equal amount of inversion has taken place. So the channel has got inverted. Yes, yes,
Yes.
yes.
At
Yes,
the
at
surface
the
region,
surface region,
the channel is
the channel
inverted.
is inverted.
Yes, yes, ma'am. Yes, I got it. So then basically, I think it is a structure of a PMOS because for NMOS, I think it bends downward.
But
So I think
But
how you can tell
how you
that it
can
is
tell
P
that it
type,
is P
EC
type,
and EF,
EC and
Fermi
EF?
level you can
Fermi
see
level
here.
you can see here.
This side, na, you
This
have
side,
to
na, you
see.
have to see.
yes,
It was
Fermi level
tailwind.
is
It was
towards the
tailwind.
This is the
conduction
This
band.
is the
intrinsic type.
intrinsic
Okay.
type. Okay.
If it is
If
towards the
it is
conduction
towards the
band,
conduction band,
then
So it
which
is
type?
N type.
which
This
type?
is N type.
This
N
is
type.
N type.
N type, madam,
Okay.
N-type.
Okay.
And if
And
it
if
is
it is
valence band,
valence band,
then it is P
then
type.
it
But
is P
here,
type. But
P
here,
type.
P type.
Yes,
which?
yes.
and here,
And
So it
here,
is N type,
N
NMOS.
type.
N type.
And also there
And
is a
also there
inversion
is
is
a
happening,
inversion
na?
is happening,
Here
na?
B,
Here B,
5B.
5B.
Yes, 5B and that 5B is
Yes.
equal. So
Yes.
amount,
Yes.
same
Yes.
amount of it is got
So this
inverted.
is
So this is
inversion.
inversion.
So can we move
So
toward the
can we
next
move toward the
question?
next question?
Yes, ma'am.
So
So
in MOS
in MOS
capacitor
capacitor with an oxide layer thickness of 100 nanometer, the maximum depletion layer thickness is 100
The
nanometer. The
permittivities of the
permittivities of the
semiconductor and the
semiconductor
oxide
and the
layer are
oxide layer
ES
are
and
ES
EOX
and EOX
respectively.
respectively.
Assuming the
Assuming the
ESY,
ESY
EOX is 3,
EOX
the
is 3,
ratio of
the
a
ratio of a
maximum
maximum
capacitance to the
capacitance
minimum
to the
capacitance
minimum
of a MOS
capacitance of a
capacitor
MOS
is,
capacitor is.
so at least
Okay, at
calculate
least
the
calculate the
Cmax by Cmin
Cmax by
value.
Cmin value. There is not that much time,
So I'm giving
so
some
I'm
hint.
giving some hint.
Yeah, just Cax is equal to epsilon x by Tx, madam.
Okay, Tox is
Okay,
given
T
here.
is given
Okay,
here.
100
Okay, 100
100 nanometers,
nanometer.
madam. 100
meter.
And
nanometers.
maximum
A
thickness
maximum
also
thickness
given.
also given. Maximum
I mean
thickness, I mean
Dmax,
D max,
right?
right?
Yes, ma'am.
D
Dmax
max is given,
which is also
which is
100
also
nanometer.
100 nanometer,
And ES by
and ES by E
OX is also
OX is
given.
also
So
given.
you have to
So
find
you
out
have to
the
find out the
Cmax
C
by
max by
CV.
C mean. Okay,
And which is
and
you
which
can
is you
write
can write EOX by TOX by EOX by TOX into ES by Tmax by EOX by TOX plus. You can also check the formula. Okay, and just put the value. Cmax by C mean equal to 1 plus EOX by TOX into Dmax by ES. Now here I am writing. The value is 1 plus 1 plus 1 by 3 into 100 by 100, and the value is 1.33. You can cross check the answer. 1.3. All the value are given, just you have to know the formula how to calculate and just put the value. Write down, then we are going to move toward the next question. 8 minutes left. can I move towards the next question?
Yes, ma'am.
Pradeep, Samuel.
Yeah, yes, ma'am. Yes, ma'am.
Okay, the question number 20. So in N channel depletion MOSFET has fallen 2 points on its ID VGS curve. VGS equal to 0 at ID equal to 12 milliamps and VGS equal to -6 at Z0 equal to infinity. So which of the following Q points will give the highest transconductance gain for the small signal? First option is -6 VGS, second option is VGS -3, and VGS equal to 0, and VGS 3. Can anyone tell what is the difference between the depletion in depletion channel MOSFET or enhanced mode MOSFET?
In
Yes.
ma'am, in depletion mode, the channel is induced.
Yes.
Channel existing, madam, even at VGS 0 volts also, that is depletion. Even for VGS greater than V threshold, the channel is created, that is enhancement.
Okay, in enhancement mode, there is no channel. We have to give some input voltage, VGS value. So, we have to create the channel or make the channel, right? And in depletion mode, already there is a channel present. We have to give some gate voltage to stop or to deplete this channel, right? Hello.
Yes, ma'am. Right option. Right, ma'am.
Okay, so here in channel depletion MOSFET. Okay, so channel is there, and also there is a two condition is given. When VGS 0, the ID is 12 milliampere, and the VGS is -6 volt. Then Z0 equal to infinity. So, like here you can see, if we plot this, the VGS, this is the ID value, drain current. Okay. So VGS 0, there is some current is present, 12 milliamps, and it is in channel depletion. Like if you can see, there's source and drain. Like if you are taking source and drain, already here the negative, and this is like N plus. Okay. So here the channel is present. And if you are giving some positive voltage, no, VGS positive, so it will, if it is N type, sorry, N type or P type, like if you are giving the some positive voltage, so it the electron will like comes towards the surface, and also the current value will increase. So this is the curve. And also after that, when you are giving some positive, the slope will increase like this. Then suddenly it will rise. Okay. So here -6 voltage. Then resistance and inflating. It means 0. 6 voltage, and here 12 voltage. ID is 12 voltage. Okay, so if you are giving positive voltage now, in that case also you are getting the higher current. So what will be the right answer here? What option?
First option.
The Q point. Carefully see the structure and the question. Which of the following Q points will give the highest transconductance gain for a small signal? It means transconductance gain. What is the transconductance? Tell me. GM equal to
ID by
what is the
VGS.
till ID by del VGS. Okay. If you are taking, and a small signal, it is only a small. Okay. So small amount of voltage you are changing, you are getting the higher current change. And in this region, when you are giving the, see here, when you are giving the positive voltage, no? So already here the NN is present, the channel is present. Also it will attract more electron towards the surface, no? So current will increase rapidly in that region when you are giving the positive voltage. So when in the positive region only the current will increase rapidly. It means del ID, the change in the current is change in the current is increased only when the voltage is positive.
Are you getting my point?
Are you getting my point?
Yes.
Pradeep?
Last option will be the right answer.
Yes.
Yes.
Pradeep and
Pradeep
Kavya?
and
Yes,
Kavya?
ma'am. Yes, ma'am. Yes, ma'am.
Like it is in channel, so when it means in channel depletion MOSFET, it means there is a already channel is present when you are not giving any current voltage. Okay, your in VGS is 0, in that time also the channel is present, and when you are giving some positive voltage, it will attract more electron towards the surface. Okay, so the current will increase rapidly when the VGS value is positive.
And here
The Q point will give the highest transconductance. So transconductance will high when the VGS value is positive. So only the fourth option, the VGS value is 3 volt is applied. So in that case, we are going to get the highest transconductance gain. Okay.
Fine.
So this is the
question number 21. In the circuit shown,
the
threshold voltage of each NMOS transistor is 1 volt. Okay, threshold voltage is given, and ignoring the effect of the channel length modulation and body bias, the value of V output 1 is.
So you have to find
out.
Ma'am, 1 volt is the answer.
Okay. Can you?
Yes, madam. 3 minus 1 minus 1, madam. 1 volt is the answer. It's a simple pass transistor concept, madam.
So if you can,
in this point also,
2 volts, madam. 2 volts. 2 volts.
We are getting 2 volts now. 3 minus 1 because 1 is the threshold voltage, so we are getting 2 volts. So here this 2 volt is applied and 1 is threshold. So here what we will get? 2 minus 1.
Option C, madam.
1 volt. Okay.
So this is
the last question. Statement is in the linear region, operation of MOSFET drain current decreases as the temperature increases. So is the given statement true or false? In the linear operation of the MOSFET, if you are increasing the temperature, what happens? The current will decrease or increase. At first tell me mobility mu. It will increase or decrease.
Mobility will decrease with the increase of temperature, yes.
Then conductivity? If mobility decreases, then what about the conductivity?
Conductivity will also decrease because conductivity is dependent on mobility.
And if conductivity decreases, then what about the current?
Current will
Current
also
also decrease, madam. Current also.
Okay. So this is statement?
True.
Yes.
True statement.
True, madam. True, madam.
So the right option is true. Okay. So up to this, we will meet again next Tuesday, 7 p.m.
Thank you, ma'am.
Thank you, ma'am. Thank you, ma'am. Very interactive session. We understand that.
Thank you, madam.
Okay.